I'm back. We're going to do 1B, so we are going to use L4 to approximate the area here. And you'll see what happens when you use the left endpoint, okay, of each subinterval. So take a look at this. I'm down here now, left rectangles, and I started to use decimals. So we still have 0 to a fourth, which is 0.25, and 0.25 to 5, 0.5, and 0.5 to 0.75, and 0.75 to 1. So I put all those subintervals down. You can pause this if you're taking notes. Now we're going to use the left endpoint. So I have to use x equals 0. The left endpoint here is 0.25. The left endpoint here is 0.5. And the left endpoint here is 0.75. And those are going to be the four rectangles. Now, if I use this left endpoint on this first one, the height, notice, is 0. So I have this rectangle here that has a height of 0. And then I use, on the next subinterval, I'm going to use the left endpoint as the height of my rectangle. So I get this. All right. See, different. Right endpoint, left endpoint's different. So now this one, if I use the left endpoint, I come up to, on this subinterval, you get that. And this last one, I use the, pardon my slanting, there you go. So quite a little bit different from here. We're using the left endpoint of each rectangle. And the left one here is f of 0, will be the height of that one, which we know is 0. F of 0 is 0 when you plug 0 in here. 0 squared is 0. And this one's f of, what was that, left-hand endpoint, 0.25. This one is f of left endpoint, 0.5. And this one's f of left endpoint, 0.75. And you don't even use f of 1 when you're using the left-hand endpoints. Now I'm going to come over here and figure these areas. I was doing all kinds of messy stuff with decimals earlier, excuse me. So if I take the width, and the width of each one is 0.25. 0.25 times 0 is 0. 0.25 times it, and then I plug the 0.25 into the function, and I'm getting 0.015625. Now, since we're doing estimates, I'm going to go ahead and take the decimal places all the way. And 0.25, and this is 0.25, you get 0.025, 0.25, and this f of 0.75 is 0.5625, and that gives you 0.140625, and I add those, and that gives you your L4, which is 0.21875, and that is an underestimate. So we have an overestimate where it's more than the area we're looking for, and this is less than the area we're looking for. If I flip this over, I wrote that the S, now remember S is what they're calling this, under the curve, we know that it's going to be between these two values. So we've at least narrowed it down a little bit. And the theory is, and I'll do this theory before we get to the midpoint rule, is if you take n to be larger and larger. So let's look at this one. This is a right-hand endpoint. I took this from the book, so it's a little blurry. This is n equal 10. R sub 10 is 0.385. So this is taking the 0 to 1 and dividing it in tenths. So, you know, it's going to be 0.1, 0.2, 0.3, 0.4, all the way to 1. And they get an estimate, adding up all those rectangles, the joy of that, of 0.385. Then they did 30 rectangles and got 0.3502. And then they did 50 and they're getting 0.3434. And notice that the more rectangles you divide this into, the better of an estimate of the area under the curve you're getting. And then they did the left endpoint as well. They did n equals 10 rectangles, 30 and 50. And look, this is 0.3234, 0.3434, so we're getting a better estimate. As a matter of fact, I think I wrote up here we can approximate the area better by increasing the number of rectangles n. As n goes to infinity, r sub n goes to L sub n, so those become equal, and that gives you the true area. Now, definition. The area of the region S that lies under the graph of a continuous function f on the interval a to b is the limit of the sum of the areas of n approximating rectangles, and we can write a is equal to the limit as n goes to infinity of r sub n is equal to the limit as n goes to infinity of L sub n. All right, I'll be back for the midpoint rule.